Hello and welcome to this Ignite Summit session on SQL development, tuning and troubleshooting in Apache Ignite. My name's Ian Ruffell and I'm a Senior Solutions Architect here at GridGain. So what we're going to look at today is an Ignite SQL overview, so how Ignite handles SQL, some of the diagnostics tools we can use, and then we'll look at some analysis examples. And we'll move on and have a look at what some of the typical SQL traps are, and come up with an optimization checklist. And then we'll have a quick look about what's coming in Ignite version 3. So Ignite SQL supports the syntax of SQL 99. It means you can use regular SQL queries, but it doesn't mean that all of SQL 99 features are currently supported. However, we do have distributed joins, aggregations, and sorting all supported. And you can change your data schema on the fly, so it's possible to alter tables and create and drop indexes. So Ignite SQL transparently works with both in-memory and data on disk. So let's have a few words about how queries are executed across an Apache Ignite cluster. There are no dedicated nodes for that, so all of the server nodes in a cluster participate in the query. So the SQL engine resides on every single node, and the actual query is being executed as close to the data as possible. So that's how we achieve our speed and scale. And the cluster does its best to optimize for this. So let's have a little closer look about the subsystem responsible for execution within a node. It's the main part of the query engine itself, and we often say that it's the H2 engine is utilized for that. That's not 100% true. Our engine is based on H2, and for example, the GridGain Community Edition and Enterprise and Ultimate Editions actually have a forked version of the H2 engine because it does some special things to optimize queries. So the engine is plugged into index structures created for SQL. The index structures in turn reference key value partition store. So in general, it's pretty fair to say that the engine uses index structures only, but sometimes it could fall into the partition key value store if indexes are currently being rebuilt and therefore unavailable. So the current engine uses a MapReduce paradigm for distributed query. So every query consists of two main parts. There's the map part and the reduce part. So the map queries will be executed on every node that stores data for a query. The reduce phase then will be executed on the node where the query was initiated. So for thin client, that will be the node that's serving the connection for that client. And a process dedicated to dividing a query into those pieces is called split, and the module responsible for that is called the splitter. So let's have a little closer look about that. So it consists of two major parts. So there's the H2 engine and the Ignite SQL engine itself. So H2 is responsible for local per node execution, and the Ignite SQL is responsible for query orchestration. So in fact, there should be an arrow from every Ignite component into the H2, as it's used in every step, more or less, of the query. The only exception is a simple parser for Ignite-specific commands. So for example, the splitter, first of all, calls H2 to get a plan for the query. What's really important here is that all the data is stored in Ignite and wrapped to H2 iterators. So H2 only duplicates some schema information in order to make parser, validator, and planner work. So now I'd like to have a little look about Affinity, and we'll need this later if we've got partition tables. So what we have is a key, and we use some function of the key to spread data across the cluster. So in this example, cities from the same country have the same color, but you can notice they're shuffled across the nodes, and that's not very good or not very bad, but we might be able to improve that for certain types of queries. So let's imagine a situation where we want to manipulate this layout and achieve a better performance for our query. So we do this by defining an affinity column for that. So in this case, what we're going to use is the country ID as our affinity key. So you see in the DDL there, we've got with affinity key equals country ID. So there's several useful flags we can use when defining a query. And classic DB users can use these as a hint. So lazy equals false means that the data is accumulated in memory, and the user only starts receiving data when the query is finished. So that can use up a lot of heap space if you've got a large result set. So with lazy set to true, the engine does its best to process and transfer the results iteratively and as soon as they're available. So it can be much more efficient and use a lot less heap space. Enforced join order prevents the query optimizer from changing an order of a query. Distributed joins, so by default, there's an assumption that everything is co-located and it's okay to join locally. But should this not be the case, distributed join works with equi-join only, and indexes should be present on fields used for joining. Co-located, so it should really be called co-located group by. In general, that means that all data for aggregation is available locally, and it should be done locally. So skip reducer on update, so works with updates and allows you to make in-place manipulation calls on a mapper. And we'll need some of these flags later when we have a look. So let's have a closer look about the current SQL engine capabilities. So index pickup could be optimized, and sometimes the engine is able to take care of a join order. There's a static optimization reorganization subquery to join when it's possible to do that. Memory tracking and offloading, so this feature doesn't exist in Apache Ignite, and I don't think it's going to be introduced, but this is one of the things that required the H2 engine to be forked for the GridGain editions. The current MapReduce drawback is that only one MapReduce phase is possible. It means that we can't calculate an aggregation in a distributed manner and then transfer it back for another query as a clause. There's an initiative to re-implement the engine, and it's being developed at the moment. You'll see that in Apache Calcite is going to be used in Apache Ignite 3 and GridGain 9, and we'll put a little link in there. You can go and have a look at that yourselves. So next, let's have a look at some of the diagnostic tools that we can use. So some of the diagnostic tools that we've got available to us. There's a query plan, so we can see exactly how the system has decided to execute the query. There's some system views that we can go and look at various bits of information about queries that are running, how long they take to run, and all that sort of thing. There's then some metrics that we can view. There's also tracing, so we can see the various different parts of a query and how they're executed around the cluster and timings associated with those. And then last but not least, there's obviously logs that if there's hints on a query, they can show up in there. So all of these things are inside GridGain Control Center, and we'll pop over now and have a quick look at that and see some of the tools we can use. So this is GridGain Control Center. As you can see here, we've got our cluster management page. So we've got 2 nodes in our cluster here. We also have the ability to create dashboards. So there's a number of predefined ones that we can use. So there's templates for those. You can see here we can very easily monitor the CPU load, the heap size in each of the nodes in the cluster. You can see here we've got tracing, so we'll come back and have a look at that a bit later. And then we can do SQL queries. We can use this kind of notepad here to develop our SQL queries. We can have a look at the schemas we've got defined. So you can see here we've got our city and country tables. And while we're here, let's just have a look. So this is this is the data loaded without an affinity key. So we can execute that query, and you can see we've got 81 cities from the country GBR. So if we execute that on a particular node, we can find out how many keys are on a particular node. So you can see we've got 41 on that node. Let's just select the other one, and we should have 40 on that node. There we go. So if we now reload the data, using an affinity key, we can see the difference that that's going to have now. So again, if we execute on all nodes in the cluster, you can see we've got 81. If we select a particular node, select that one first of all, and rerun the query, you can see we've now got 81 cities from GBR on that particular node. If we go on to the other node, we can see we've got no cities on the other node. So what that means is we've defined an affinity. So when we do a query against the city table using that country ID, it's only going to go to the one node to get all that data. So again, it's all about moving less data around the network. Okay, so let's go back and have a look at the slides now. So we can use the explain keyword to show how Ignite is going to execute the query and look at the execution plan. So just putting that explain prefix into the query and running it, you'll see that we get the two phases. So there's the map phase and the reduce phase. So for this particular query, it would be just 2 rows, and the last one was always the reduce part. So in this case, it looks pretty good because it leverages an index on IDX 0. You can see that here, public IDX 0. And on the reduce side, it's pretty minimalistic. And the merge scan here means that the reducer is trivial and effective. So it'll only fetch and merge partial results from the mappers. So let's have a look at a slightly more complex query now. So we're going to get the name and population of countries that have an average city population above some predefined argument. And this one is meant to reproduce a case where intermediate results are being passed to another part of a query. In our case, it's a distributed join. So the map queries. So here you can see the situation when there are 2 map queries, and the query splitter decided to split the original query into those 2 queries. And these are being executed independently during the map phase. The reduce phase uses both results. So the first one projects into a virtual table we'll call T0, and the second one projects into another table called T1. So let's keep that in mind when we look at the reduce phase in a minute. So what information can we extract from these plans? So you can see the indexes proposed to be used by the engine. So in our case here, we've got city country IDX. In this case, we can see that aggregation is really effective because of the sort-based algorithm that it's going to use as a hash-based one. So you can see here we've got index sorted. So in the reduce phase here, you remember we talked about virtual tables, and you can see here that we've got those virtual tables T0 and T1 being used as part of that query. So this plan is pretty big, but you can hopefully pick out the actual join order. So we remember what the corresponding map part looked like, and it seems like the entire country table is being retrieved here. There's no filtration on the mapper side. And in this case, that's not really a big problem because it's a pretty small table with only about 200 entries in it. But just keep in mind, if that table was big, then this pattern would trigger a lot of memory usage, a lot of memory pressure, network pressure, and the reducer will need to hold a copy of all that collected data cluster-wide. So the moral of the story is here, know your data. So just a little summary then. So what's the query plan useful for? So looking at the join order, looking at index usage, and looking about the distributed query split, so the map and the reduce phases. So system views, you can see the documentation link there. But basically what we'll do here is just do a select star from sys.views, and it'll list all the views that we've got available to us. And we'll have a look at some of the most useful ones to do with tables, queries, and connections and metrics and so on. So tables and table columns will show us clearly the schema and tables that are defined. It'll also show us the affinity keys if that's been defined, and any particular field types. And the indexes table will show us the fields, the indexes that are defined, and the inline size of those indexes as well. Then SQL queries, so that shows us the queries that are currently running on a particular node. Then metrics, so again the metrics are fully documented, and we have various exporters, so we can see them via JMX. We can select via the system sys.metrics view. It's also fully open census compliant, so we can use the open census API, and in fact the GridGain control center also uses the open census APIs to display those metrics. And then finally we have logs. I'm sure people are familiar with logging, and can adjust various logging levels as well. So what are the metrics are useful? So one of the key ones is index.io. So that actually gives us a list of statistics about all the indexes and how they're being used, how often they're being used. Then we've got prepared query. So when you execute a query, it actually caches the query plan for that. So if you run the same query over and over again, it hasn't got to redo that particular phase of the operation. Then we can have a look at memory. So in the SQL memory quotas, we can have a look at free memory, offloaded queries number. So that's the number of queries that are being offloaded onto disk. So if your queries suddenly start going slowly for some particular reason, have a look at that, because it might be offloading onto disk if it's running out of memory. Then next up is tracing. So we saw the tab on Control Center, and we're going to have a little look at that in a second. It's fully documented again in the Apache Ignite documentation. It's based on open census, and there's a standard tool for looking at this, which is called Zipkin, so you can export to that format. But we've got it all built into Control Center. So let's just pop over to Control Center and have a quick look at how that works. So here we are back in Control Center. We're going to have a look at the tracing now. So first of all, we need to configure our tracing. So here we're going to switch on the SQL tracing. And you can see here, we're going to trace 100% of the queries. If you're running this in a production environment, you probably wouldn't want to do 100% because there's quite a lot of additional workload on the cluster to collect these traces. So let's enable that. Let's go and execute a slow query. So what we've got here is a little custom SQL function to simulate a slow query. So let's just execute that. It should take about 5 seconds to run that query. And there we go, there's our results. So let's pop back now to the tracing tab, and you can see here, this is our query. And what you can see now is that the all the different phases for the query on the different nodes. So you can see here that the execute is happening on the two different nodes here, and you can see that this prepare phase during the execute is the one that's taking all the time. So we can very quickly and easily go through this and see what's taking up the time and optimize the query potentially, depending on what's happening there. It might show that we've accidentally done a full table scan, for example, so we can then optimize our query to speed things up and prevent it pulling so much data out. So next up is the logs. So again, fully documented. There's a link there. It can be useful if you've got any errors. You can quickly see exceptions on the map nodes, any warnings, maybe about long-running queries or queries with a big result set that's causing memory errors, and also get the inline size as well. So logs can be tuned at runtime by using JMX. So a couple of ones to look at there. So there's the long-running timeout multiplier, so that defines how many times the messages are repeated, and the threshold for those as well. So here's an example of a long-running query message in the logs. So you can see the query is taking 2 and a bit seconds there. You can see the type of the query. In this case, it's the map phase, and its type. So whether it's, in this case, it's not a distributed join, the enforced join or is set to false, and also lazy is set to false. So you can see here now we've got scan count and a lookup count. So scan count of 4 is pretty bad because it means it's scanning the table 4 times. You can also see in this example we've got a very big result set. In this case, it's produced 320,000 results. Okay, it's run pretty quickly for that, but you know, our scan count's very high, and particularly on the on the result set there, you see. And this example, we've got our inline size, so we've got our table name and the index it's using. We can see that the current size of our inline is 10, but it's recommending it should be 98. So that kind of hints that we need to go and adjust the sizing in our indexes. Okay, so let's have a look at a few analysis examples. So this query we've got here, it works okay with a single node, but it breaks for multi-node installations. So experienced Ignite users might have already understood what the problem is here, and it's all about co-location. So in this example, the join happens by country ID. So let's query a system view and try and understand the actual Affinity layout and what we can see here. So we can see the country ID is not the Affinity column for the city table. So let's keep that in mind. So here's another example triggering wrong query results. This one fails even on a single node cluster. So the root cause here is an optimization allowing to go directly to the right partition in case there's a corresponding clause. So here's another example of triggering wrong query results. So this one fails even on a single node cluster. So the root cause here is an optimization allowing it to go directly to the right partition in case there's a corresponding clause. So maybe you've already guessed what the actual reason, and here it is. And here's a link so that you can get more information. So it's all about partition pruning. So let's move on to the next one now and have a look about schemas. So we've already figured out how to fix the previous two there by putting the correct Affinity key on. And in this case, it's on the country ID. So the second one is to make the table replicated. And a replicated table means that all of the data is stored on all of the nodes in the cluster. And it could work in this case. You've got enough capacity because it's a fairly small table, and that cache will then be stored on all nodes in the cluster. So in this example here, we can see we've got interoperability between both the Ignite SQL API and the Cache API. So it's can be a very powerful tool, but with great power comes great responsibility. So it's pretty straightforward to get sizes diverged here. So by sizes, I mean the size of the cache. So the index structure in this example observes only ID 0 and ID 1. So the additional field we've got there is going to be hidden. So the Ignite SQL engine can calculate the inline size automatically, taking some internal information and considerations into account. And in general, there's no good solution for that. It's always a compromise. So for every entry in the index has a constant size, which is calculated during index creation. And this size is called the index inline size. So obviously, it's a compromise between speed and size of the index. So just to understand the different field types and how big the indexes get there, there's always one byte dedicated to a tag, and it stores the type information. And in other cases, it's enough to maintain this effective tree structure. So for example, an integer has a size of 5, so it's 1 for the tag and 4 for the actual value. And then, for example, a varchar is 1 for the tag, 2 for the size of the variable length field, and then obviously the actual text itself. So let's have a look at index records in deep. So to ensure that records are truly unique, primary key columns will be added to every record. So Ignite doesn't store a row ID, but it's extremely complicated to maintain such a structure in a distributed solution. So how does it physically work? So the index structure should store records of a fixed size in order to be performant. So at this point, nothing super intelligent happens. The engine will recommend the length of the affected line, and the most selective column should come first. If we need an index containing a string that are constant prefixes, then we definitely need to add a prefix length to the inline size. Otherwise, you can get into double trouble, and you'll neither have a small cozy index or any speed up improvement, as the index will be totally polluted with constant values. So let's have a look at a little example. If you need to store a file path for information, for example, we're going to create an index on this path column in our table, but what size should we use? So there's a constant prefix here, which is the folder 0 is folder 1. So an inline size of less than 17, so that's the 1 for the tag, the 2 for the size, and 14 for the actual text, won't be very useful, and it's going to waste a lot of memory. So in this case, we've got an ID, and it's got only very few unique values, so it's not very selective. So in this case, having an inline size of less than 23 is not going to be very useful. Again, we're going to be using 1 for our tag, 2 for the size, 3 for the constant characters, and then 1 for another tag, and 16 for the UID. So in this case, our recommendation will be to have 23 plus the inline size of the order number and the inline size of the primary key. So in this example, we're going to have a look for queries that are using a lot of memory. So we saw previously we've got the sys views. So in this case, we're going to use the sys.SQL queries history and look for queries that are using a lot of memory. So you can see here we've picked out a query, and it's not actually using an index. So what we can do here is tell it to use a particular index, and hopefully that then will improve our memory situation and avoid doing full table scans, for example. So lazy execution mode, again, we had a brief look at this earlier. So if we've got lazy set to false, we accumulate the result set in the heap when the query is executed. So when the query finishes, then the result set is ready to be used. So if we set lazy equals true, then we can use the an iterator pattern or paging, for example. Obviously, that's only when the H2 engine can actually do that. So it's not a silver bullet to reduce memory usage. The performance impact for a tiny result set is very minimal, and it's not implemented yet for the reduce phase. So in the GridGain additions, we can configure some memory tracking. So one of them is SQL offloading. So if that's enabled, we need to pay attention to the group by. So it's good for sorting, but bad for group bys. And then also we've got memory quotas we can define. So by default they're off, but we can set them up to prevent queries from using lots and lots of memory. Okay, so let's just have a look at the typical SQL traps, and we'll come up with a checklist for those. So first one, data co-location. Remember to be mindful of that when you're doing distributed joins. The data might not be on the node where you think it is. Lazy execution mode, so that can be helpful for memory and also speed up getting some of your initial results back. And then look at your index usage. So using the explain, look at the plan and hints, and use the use index hint wherever possible. Then there's the join order, so we can use the enforced join order if needed. And then looking at the index inline size. So we saw also how that can have a big impact on performance. Making sure that we've got a good size there, and looking at the hints if that's incorrectly set. And then there's other simple optimizations we can do. Maybe instead of using an OR, we can use a union OR. So a couple of useful links to finish up. There's a page on SQL performance tuning, which goes through a lot of this stuff, maybe in a little bit more detail than we have here. And then I would urge you to also have a look at there's a session on the new Apache Calcite framework that's going into GridGain version 9 and Apache Ignite version 3. So this should improve the way queries are executed in Ignite and GridGain going forwards. So thank you very much for your time, and that's the end of this session.
Great, thank you for that, Ian. Some good detailed information there. We did get a few questions in the chat, so we get straight onto those. So first, Niels has a question. Is it possible to get average on SQL sysview, like duration average, etc.?
So simple answer to that is yes, you can. They are just SQL views, so you can run a query against those and get an average. There's also, I think I showed you in Control Center, but there's a tab in there to show you SQL history, which has got sort of min-max average statistics on there as well.
Sounds good. And we touched on Control Center a couple of times, so I'm going to bring this one up as well. Control Center is a paid application, right?
It is. So yeah, the question about any plans to launch a community edition, and as far as I'm aware, there is not. I think the kind of common solution to that is to use the Open Census API and actually integrate with things like Grafana and Prometheus. You can achieve similar sort of things, and there are various other tools for doing SQL development, like dbeaver, for example. So I think there's a combination of open source tools that you can use, but Control Center is a GridGain product and is kind of bringing all of those useful things together into one product.
Good answer. So you talked about Calcite a little bit there. So I mean, you said it's going to bring improvements. Do you have any examples of things that might be improved, or is it just kind of generally better and we'll kind of cross that bridge when we get to it kind of thing?
So I think there's the execution plans should be much more efficient, but there's a couple of really big things in there which should get performance improvements out of the box. And one is vectorized execution. So in most of the modern CPUs, there's actually a vectorized way of executing data in parallel on the CPU directly. Currently, Java can't take advantage of that, but with a dedicated engine attached to Calcite, we will be able to take advantage of that, as well as some hardware improvements. So we'll be able to take advantage of things like GPUs as well, which also have the sort of massively parallel execution engines, and it's also extremely fast memory.
Cool. So looking forward to those in Ignite 3. Another question, unless you just come in. Does this, I assume kind of really means Ignite's SQL engine understands that past queries are no longer valid, like when the data itself changes or skewed, etc.
So I think the data changing shouldn't invalidate a query. It's if you change the schema, it would. So if you drop or create a column, for example, that would invalidate it. I don't actually know the answer to that question, though. So I don't know if you know, Stephen.
I mean, the query executes at a point in time, doesn't it? So it's not like the data can be invalid at some point.
Yeah.
Like a continuous query. So if you have a continuous query which listens to changes in a table, that would be invalidated if you change the table, and it would tell you when data itself changed. So yeah, I'm not sure either. If you get any clarification on that, do let us know. So maybe one or two final questions. So what would you say is the most common mistake people make when they're running SQL queries on Ignite or GridGain?
Yeah, so I think we kind of touched on that during the talk, but one of the most common one is the distributed join, and understanding that by default, Ignite assumes that you've got all of the data on the local node, so you can end up with joins that haven't given you the right result sets. So that's the first one to look at. Another one is just knowing your data and recognizing when you might force a full table scan, because a full table scan can have a dramatic effect on the performance of a query. So generally, if you've got anything in the where clause, make sure that column has got an index on it. And I guess finally, talking about co-location, look at your data and look at the distribution of your data, because if you've got very different sizes of the groups of that co-located data, so say in the city example I had there, you were comparing the number of cities in the US versus the number of cities in a very small country like I don't know, Monaco, which probably only got one. You can end up with a lot of data on one node and not much on another node. So you might want to think about distributing it or co-locating it slightly differently in those cases.
Sounds like good advice. Abhinav kind of clarifies his query and says he's talking about kind of indexes, the past query is cached, for example. So I think the short answer to that, without wishing to steal your thunder, Ian, is just that Ignite manages that all for you. You don't really need to worry about that. It will automatically invalidate it if it needs to be invalidated, but it probably doesn't.
Yeah.
So I think maybe one final question. Deji, again, apologize if I'm mangling your name, asks, does the order of columns in a where clause still matter?
I don't think so. As long as they're all indexed, then the performance should be good regardless. But I think one thing is if you're doing a select, just kind of select the columns that you actually want rather than just doing a star. You'll get much better performance.
So slightly leading question is how many indexes per table are used in a query?
Good question. I think as many as possible. But obviously, if you have too many, that can actually degrade performance.
But sorry, what I was getting at is like when you're doing a select query, how many of the defined indexes does get used in a particular query?
Don't know.
So sorry, that wasn't supposed to be a trick question. So you can define as many indexes as you like on a table, but when you execute a query, only one index gets used per table at a time. So if you have an index on column 2 and another one an index on column 3, only one of those two indexes will ever get used in a particular query. So you might need to use the composite index to cover both of the columns if you do where something and something else.
Or do subqueries.
Yeah, something like that. Sorry, that wasn't supposed to be a trick question.
That's all right.
Well, thank you again for your talk. I think it was really good and interesting. Any kind of final words?
No, I think just to reiterate, thank you everybody for joining us, and yeah, it's been a very good learning experience, certainly for me.
Great. Well, thank you, Ian.